This conference will now be recorded.
Good morning, everyone. Thank you for joining us today. I see that already participants are starting to join in. Thank you. And we'll get started and explain some of today's functionalities and the content. Some participants continue to join us. So as you know, this training session is in the frame of CoEXist final conference. We've had sessions yesterday afternoon with great participation, and then today again in the afternoon we'll have the second part of the conference. If you'd like to join and have not registered yet, please let me know in the chat box. And then this morning we have the automation ready modeling training session. Before we continue with that, let me let you know a bit about the GoToMeeting functionalities. This is a bit different from what we had yesterday if we also joined with the GoToWebinar. In this case, we have a smaller group, but you can still choose to connect either via computer audio or by phone call. And when you press on the phone call, you can see different countries which you can select for when you decide to share, to connect via the phone call. You also have a mute button similarly to GoToWebinar and a chat box. Initially, we'll have everyone muted and we'll mute you if there's any background noises as well. But there's going to be a moment during the training where we'll encourage audience participation and we'll unmute participants to ask questions and to go through the exercises. You can also see the full list of attendees and contact us either directly or to everyone in the chat box. The theme for today is Peter Sukennik from PTV Group, who's going to be your trainer, and myself, Daniel Franco, who's going to be supporting you on the technical side. So if you have any trouble with the GoToWebinar, GoToMeeting functionality, please just contact us via the chat box and I will be happy to help you. The training session is going to go on until 12 today, starting with a bit of an introduction to the modeling tools, demonstration, and some practical examples. And I wanted to remind you that if you want to learn more about the automation ready functionalities, please follow this link and see the webinars that we've recorded throughout the project. Also contact us via the website if you have any other questions. With that, I would like to leave you with Peter Sukennik for the training. So I'm going to give you the moderation now, Peter.
Good morning, everyone. Welcome to our workshop about how to model automated vehicles in Vissim. This should be a workshop. It means it should be interactive in some extent as much as possible in this online format. So if you have any questions during my presentation, then let us know, use the chat, and you should be able also to speak to me and to all attendees. This should be also possible that you can share your screen, and you also can let me to control your mouse and keyboard if needed to resolve some problems in your network. After the presentation and after the exercises, there will be at least 30 minutes to discuss your modeling problems and your questions. I'm Peter Sukennik. I work as a product management manager for PTV at the headquarters in Karlsruhe. And let's start. I will switch off the camera and I will continue with the presentation, and I will switch to Vissim afterwards. A few more instructions for you. The best setup for you would be to have 2 monitors and use 1 monitor for the stream so you can watch what I'm doing. And on the second monitor, you should have Vissim open, Vissim 2020 version. So you can do the clicks with me, because I want to do some exercises with you, and you will have the opportunities to do some clicks with prepared examples I already shared with you. So I sent you, or Susan sent to you, some links where you can find examples. I hope you downloaded these examples. If not, please do it now, because we will use them. So the agenda for today. At first, I want to talk a little bit about the stochastics in Vissim, because there are 2 types of them. Then we will have a look on the new features we implemented within the CoEXist project. We will do some exercises, and we will have a look on some examples. Then a few information about the driving behavior parameters for AVs in Vissim, and how to deal with cooperation and communication capabilities. And as I mentioned, at the end, there will be time for your questions and for your modeling problems. So the explicit stochastic is a stochastic which can be influenced or changed by the user directly, whereas the implicit stochastic is that one which is a part of the code but cannot be changed by the user. What does it mean? Typical way for applying the explicit stochastic is using the functions. For AVs, we can assume that they will behave more deterministically in comparison with the human drivers. And to reflect that, we can set appropriate desired acceleration and deceleration and maximum acceleration deceleration. So you can set the median values and the minimum and maximum values. Each vehicle in Vissim gets an individual values from this range. And for AVs, you can reduce the speed of values if it fits your assumptions. So let me switch to Vissim now. You should see my Vissim screen now. And I was talking about functions. And let's have a look on desired acceleration, for example. So when I double click in the list on the car, it opens this window where you can see the median line with the points and the maximum and the minimum points. And if you need to change these, you can move them by using your mouse. Or the other way how to change them would be to use the list, where in the coupled list data points, you can see all the points. And if you don't want to have the spread, then you can just copy the epsilon values and insert as a minimum and maximum values. And in that case, you will get just one line if you don't want any spread. Of course, you can have some spread there, but a little bit smaller than for conventional vehicles or any which fit your assumptions. And you can see there are many other functions you can have a look on. So there are the second typical place to set explicit stochastic in Vissim are distributions, and most important distributions are the desired speed and the time. That has an impact on headways with Wiedemann 99 model, for example. And for example, for a desired speed, we can assume that the speed of AVs will be much smaller and they will obey the speed limits, what many human drivers do not do, as we know. So again, if this is the original speed distribution, then your assumptions can say that automated vehicles will follow the rules and they will drive 100 kilometers on a road where the limit is 100 with much less spread. So if I switch back to Vissim and I go to base data and distribution, desired speed. So if you have this default distribution for speed 130 and you want to create your own, then you can just duplicate this one, then open it, and you can put here a new range which fits your assumptions, and you can add also your points there if needed. So that was about explicit stochastic, about functions and distributions. You can access them in Vissim, you can duplicate, change them, and use your own assumptions. Now have a look on the new features. At first, a few words about the role of driving logic. It's the logic in the form of algorithms which decide how the autonomous vehicle will behave. And this has an implication on following behavior, lane change behavior, lateral behavior, reaction on signals, and conflict resolution. And for each of these parts in Vissim, you have a set of parameters you can set. Under the CoEXist project, we work with the concept of four driving logic space. So the proposal of from Adriano Alessandrini from University of Florence, and each of them has some typical characteristics or principles. So the race safe is always using brick wall stop distance concept, big gaps, only predefined route, no lane change, no unprotected signal phase, higher lateral distances or physical separation, and these are mostly used in closed environment. Then there is a cautious, which follow the brick wall stop distance concept. We expect bigger gaps than by human drivers, and which means very cautious behavior. Then the normal one, where the behavior should be similar to the human behavior in terms of gaps and distances to other vehicles when following, when interacting. And all allowing where we can assume also smaller gaps, but still high safety and cooperative behavior, and where the communication is a precondition. The first feature, enforce absolute braking distance. The idea behind this, the vehicle can stop safely anytime without a crash, even if the leading vehicle stops instantly, which means turns into brick wall. And this has implications for following behavior. So the vehicle keeps distance, which is the braking distance needed at the speed plus standstill distance, but it also has implication on lane change behavior, where if a vehicle wants to perform lane change into lane where also other vehicles are present, then the distances in front of the vehicle and behind the vehicle needs to be big enough. So, and that reflects the braking distance and standstill distance. And it also has impact on gap acceptance or at intersections, but only for conflict areas. It doesn't work with priority rules. And here, the rear gap equals to time to brake to full stop 1 meter in front of the conflict area. I will switch to Vissim now. And please, if you didn't start Vissim until now, please do it now. Start a Vissim. And in the directory EABD examples, so let's have a look on the examples. There is a directory EABD examples, and from this directory, I will load EABD link example into Vissim. Then start a simulation. So you see here 4 links. These 2 links on the top, there are vehicles driving at speed with desired speed 50 kilometers per hour. And on these 2 links below, there are vehicles driving with desired speed 100. And when I pause the simulation, clicking on this button here, or you can press F6 on your keyboard to pause the simulation and have a look on the distances. This first link, the vehicles are using the predefined urban driving behavior, and on this link, they are using the same with one difference. The enforce absolute braking distance here is activated. So in the list of driving behaviors, when you double click on the driving behavior number 7, and then you go to the tab Autonomous Driving. There is an option Enforce Absolute Braking Distance, and this is activated for the driving behavior number 7. And this one is used here on this link and also here on this link. But here the difference to the first one is not so big because the speed is quite low. It's just the design speed is 50 kilometers. But if you have a higher desired speed in the network, then you can see that the distances are much bigger. That's because the vehicle needs much more space to brake to come to full stop in any situation. So in a situation that in a theoretical situations, this leading vehicle would turn into a brick wall instantly without own braking distance. And this principle, these options here use absolute braking distance. This is used by first two driving behaviors or driving logics we worked with in CoEXist project, RailSafe and Cautious. Okay, then let's have a look on the second example, which you can find in the same directory, EABD examples. And it's a EABD intersection. I need to stop the simulation first. And then I can load this one. I start a simulation. And you can see two pairs of networks. On the left side, that is low speed environment. And on the right side, it's a high speed environment. And you have one major flow and one minor flow with a conflict area here, which means the vehicles in the minor flow need to wait for a gap in the major flow to cross the intersection. It's the same situation in each network here, but here the default driving behavior is used, urban, but here a modified driving behavior is used where enforce absolute braking distance is activated. Yeah, the same here. This is the default one, and this is with enforce braking distance activated. And what is the impact of this? On the left, low speed environment and the difference between vehicles, between the number of vehicles which can pass through the intersection here. You can see that's the difference between this number here, at the moment 66, 68, 79, and here you can see it's more than 80. You can see it also here in the diagram on the right side. The first one shows the situation in this network. The second one shows the situation here in the second network. The third one shows the situation here. And the fourth one shows the situation here. And you can see that when you activate enforce absolute braking distance here, then you will get a lower number of vehicles going through the intersection. The number is collected here, and collection point number 3, which is this bar number 3 in the diagram. And the number here, 153, is connected with the collection point number 4, which is this number 4 here in the diagram. So this is number 3, this is number 4, this is number 2, and this is number 1. So you can see it has an impact on the capacity of this simple intersection, because if you activate enforce absolute braking distance in that case, and especially in a high-speed environment, the vehicles, they need bigger gaps in the major flow to cross the intersection. Okay, let's go back to the presentation. The next feature is number of interaction vehicles. This was available in Vissim 10. In Vissim 10, we call that number of observed vehicles. And some network objects are modeled as vehicles in Vissim, and vehicles treat these network objects as a preceding vehicle, and that is for red signal heads, reduced speed areas, and priority rules. And vehicles also treat some network objects as preceding vehicle if they have to stop. That applies for stop signs, public transport stops, and parking lots. And since Vissim 11, instead of one parameter number of observed vehicles, we have 2 of them. We have number of interaction objects and number of interaction vehicles. Why? The idea behind it is that automated vehicle can see the signals ahead, but only 1 or 2 vehicles in front of itself, because the sensor cannot see through the leading vehicles. And if you have the settings in Vissim that the number of objects is smaller than the number of vehicles, that will be the same behavior as in Vissim 10. But if it equals or is higher, the number of objects than the number of vehicles, then you will get some new limited size and interaction behavior. So you can distinguish between interaction vehicles and objects with these 2 parameters now. And the number of interaction vehicles limits the number of visible vehicles within the minimum look ahead distance. What does it mean? Let's have a look on a few simple demonstration examples. So if you have a situation like this, that this red vehicle follows some other vehicles, and you set interaction vehicles to 4 and interaction objects to 4, and minimum look ahead distance to 0. These 4 interaction objects can be seen, so this red vehicle can react on them. And number of interaction vehicles is 4, but this red vehicle can interact only with these 3 vehicles, because the number of interaction objects is the limit. So it cannot see more vehicles than are inside this main group interaction objects. Interaction vehicles are a subgroup of interaction objects. Then imagine another situation that you have that you set 1 interaction vehicle and 1 interaction object and the minimum look ahead distance 50. In that case, the red vehicle will be able to interact with all objects within these 15 meters, because the minimum look ahead distance is set to 50. So all objects within this 50, the red vehicle can interact with them. So it can interact with this signal head, but the number of interaction vehicle is set to 1. So this red vehicle can interact only with this first vehicle and not with the others. And other settings: interaction vehicles 5, objects 3, and minimal look ahead is 0. So 3 objects are visible, and all vehicles up to 5 within this range can be seen. So in this case, these 2 vehicles. Another situation: number of interaction objects 5, interaction vehicles 3. So first 3 vehicles within interaction objects are visible, and all maximum 5 interaction objects are visible. So this signal head is visible, so the vehicle can react on it. Okay, I will switch to Vissim now and to show some examples. I go to the directory number of interaction vehicles, and there is an example test for do not see through. So load this example into Vissim. And here you can see 2 identical networks, but with different driving behavior in use. And when I start the simulation and with F5, and then I pause the simulation with F6 to see how is it at the beginning of the simulation. There are 2 vehicles coming in to the network, here, and 1 vehicle coming from the north, and this 1 vehicle will park here in this parking lot, and that will simulate a situation when a vehicle is broken, for example, and cannot continue, or there's a crash. So when I continue with the simulation step by step by pressing F6, I see that this vehicle will park here, and the same situation here in the second network. And now these 2 vehicles will continue on their routes, where this first vehicle, number 3, will turn right, and the second vehicle, 5, will continue straight. And here in the list of vehicles in the network, you can see this is vehicle number 5, and you can see here interaction target type is a vehicle, and interaction target number now at this moment is number 1. So vehicle number 5 at this moment is interacting with vehicle number 1, which means vehicle number 5 can see vehicle number 1 at this moment, can see that this vehicle is standing here and can adapt its speed accordingly. But have a look here in the second one. There is a vehicle number 6. This vehicle is interacting with vehicle number 4, which is this preceding vehicle, and it's not interacting at this moment with vehicle number 2. And that's because this vehicle number 6 cannot see more than 1 vehicle. So I will continue step by step with this simulation. So number 3 will turn right, and number 5 is approaching number 1 and can stop safely here. When I have a look here down, I have a different picture. There is a crash. So I will stop the simulation and simulate again, step by step, by pressing F6, and have a look on the vehicle number 6 and on the interaction target number. It's 4. And now I press F6 to go one time step further, and it's still number 4 here as interaction objects. One more, one more, one more, one more, and I will press F6 until I get different interaction target number here. One more, one more, 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 one more, one more, one more. Now this is the moment that this vehicle number 6 can see vehicle number 2 is interacting with vehicle number 2, but the distance to this vehicle is too small to stop safely with the speed of this vehicle, what we can see. So there is a crash because the vehicle couldn't see the standing vehicle on time. So this is a demonstration of what you can achieve with the limitation of how many vehicles can be seen, or with how many vehicles your automated vehicle can interact with. And on the slides, I was talking also about minimum look ahead distance. So I will say a few words to that one. But have a look on the settings in driving behavior at first. So on this link is link number 1, link behavior type 6, and it is using driving behavior number 6 here, and the number of interaction vehicles is set to 1. Where here on urban, this link is using the link behavior type 1, and the link behavior type 1 is using the driving behavior number 1, where number of interaction object is 4 and number of interaction vehicles is 99. So all vehicles within the number of objects that here can be visible. So these two vehicles can be, the two vehicles in front can be seen, and the vehicle can stop safely. We can do one more example. So I will stop the simulation, and now I will create a new model from scratch. And please do all these steps with me. It will be not complicated, just a very simple network with one link. And we will create a situation where we have non-lane based traffic. So we have one wide road. Let's say the width is 15. And put a vehicle input here on this link. With some high volume. I will put here 5,000. And one more thing, I want to stop the vehicles before they leave the network. So I will place stop sign here at the end of the link. So I will save the model. I will switch off the labels for vehicles. So this is how it looks like. So we will do some changes. The driving behavior here, which is used, is urban motorized, or that's the link behavior type. And I need to have a look into link behavior types list. And this urban number 1 is using driving behavior number 1 urban. So I switch to driving behaviors number 1, and I will open it and do some changes. And on the tab for lateral, I will allow any position, and I will allow overtaking on the same left and from right. So this is how it looks like. It's quite a mess. Just switch to 3D to see it clearly. So the vehicles are crashing into other vehicles. Why is that? Let's have a look into the driving behavior, urban, which is used. And let's have a look on the tab following. So the number of interaction objects is set to 4. So only 4 vehicles in front can be seen, but in a situation that there is non-lane based traffic, it can easily happen that there are much more objects in front of you. You need to observe and react on that. It's typical for bicycles, for example, but also for non-lane based traffic. So now I could increase the number of interaction objects to solve the issue, or I can say that there is some minimum look ahead distance. I will say 40 meters, which means that all objects which are visible, which are within this 30 meters, can be seen, and the vehicles should react accordingly. So I don't have crashes anymore. Because the vehicles can react to all objects they should react on in the front, and there are no crashes anymore. So a quick recap what I did. I created one link with one lane, but I set the width to 15 and insert here vehicle input with a high volume, and the driving behavior used on this link, I modified it. So when you double click on that driving behavior number 1, it opens the dialog for driving behavior. And here you have the tab lateral, where I changed the side position at free flow to any. And I activated here overtaking on same lane from left and from right. And you also can specify the distances, which the lateral distances, they should be kept. And after changing to this, to this settings, I got a lot of crashes there, and I resolved that by setting the minimum look ahead distance to 30 meters. So all objects within this distance can be seen and the vehicle can react accordingly. So the vehicles can see up to 99 vehicles up front. And to stop the flow, I insert stop sign here at the end of the link. So each vehicle needs to stop and then it can continue. Okay, I will have a look on chat. Could you please show the last PowerPoint slide with the clarification examples one more time? Yes, sure. This one. What I did in the last example in Vissim, I set the look ahead distance, the minimum look ahead distance to non-zero value to 30 meters in my case, which means that all vehicles within this distance up to the number of interaction vehicles, which was 99, in my case, can be seen and the vehicle can react on it accordingly. And after our workshop, I will provide you also this presentation so you can have a look afterwards again. I see there are some other questions. Maybe I will come to that questions later after my presentation. So the next one, use implicit stochastic. The idea behind it is that the stochastic imperfection of human driving is replaced by deterministic machines. And the internal behavior model, which was developed for humans, there are several stochastic values indicating the spread of human behavior, the risk of acceptance, the ability to estimate distance and speed difference, the precision when operating the throttle and braking pedals, and for AVs, deterministic values for these parameters can be assumed. So if the attribute use implicit stochastic is false, a deterministic average value is used instead of such stochastically distributed value whenever the distribution cannot be set by the Vissim user. And this option affects desired safety distance, desired acceleration, desired deceleration, and decision points. So when to start braking and accelerating. And for these three, the user may also specify a distribution of functions, but these are not adduced automatically. Only an implicit term is suppressed. So I will switch to Vissim again. And let's have a look on another example. There is the directory use implicit stochastic, and there is one example inside. So open this example. Okay, in this example, I'm using two driving behaviors here. The default one and a modified one. And in this one, which is modified, on the tab for automated driving, the option use implicit stochastic is deactivated because by default, this option is activated. And I will start the simulation now and stop, and will explain what is this about. I have here 4 links. Here, the default driving behavior is used for the first 2, and for the second pair of links, the modified driving behavior is used. I have here vehicles in the front with the same speed of 10 kilometers per hour. So they are at the same position exactly. And I have other vehicles which drive with higher speed and will approach these vehicles here. And the labels for vehicles here are showing me the safety distance gross value. And you can see that here these 2 vehicles, they have identical speed. They have been inserted at the same moment in the network, but they have different values here. And these 2 vehicles here, they have identical values. And when I continue simulating this, so the vehicles will approach the vehicles in front, and now they follow the leading vehicle. And you can see that this value and this value, they differ. They are changing, there is some oscillation, but they are different. And here, for the second pair of links where the driving behavior has been modified, you can see that the value is the same. Always it's changing, but it's always the same. And that's because the internal stochastic is switched off here. You can see it also in the chart, but you need to select the layout probably here to show the values. And when you continue on the simulation, that you see how the values are changing, and this one and this one are identical, and this one and this one are not identical. Okay, I go back to the presentation. The next one we implemented is increased acceleration. And the idea here is AVs, especially if using car-to-car communication, can use a tight coupling with small headways. And the normal human acceleration behavior cannot use reliable information about the future behavior of the leading vehicle. So normal Vissim vehicles tend to fall behind when the leading vehicle is accelerating. And in order to allow vehicles to keep small headway, even during the acceleration process, there is a new parameter, increased acceleration. So in the list of driving behaviors or in the dialog, you can set this value increased acceleration, which means this value defines a percentage of normal acceleration to be used when the leading vehicle is accelerating. The vehicle cannot exceed its maximum acceleration. That's a limitation. But it can exceed its desired acceleration. So when I switch back to Vissim to have a look on this, when I open some driving behavior, then on the tab for car for loving model, here in this field, I need to stop the simulation. You can put some value which is higher than 100, which means increase acceleration. So vehicle which is using this driving behavior following a vehicle of this class can use this increased acceleration. So for the use of the new features like enforce absolute braking distance, use implicit stochastic, number of interaction vehicles, and increase acceleration, we provided a recommendation. So what you should set, but it needs to fit your assumptions. So if your assumptions differ, then you should change also these settings. So the increase acceleration we recommended to use only for normal and or loving, not for cautious or race safe. Headway based on leading vehicle class. What is this about? The idea here is that the headway followed vehicle depends on the followed vehicle type or vehicle class. So you can have very small distance between automated vehicles which are connected, a little bit higher between automated vehicles without connection, and even higher distance when automated vehicle is following conventional vehicles with a human driver. And you can set this in the same dialog I showed you where I set the increased acceleration and also in the list of driving behavior. So let me switch to Vissim and I will open some driving behavior just to show you where you can set these values. For Wiedemann 99, you can set CC0 and CC1 and increase the acceleration based on of the class of the leading vehicle. And you can insert here as many lines as you need and set the appropriate value here. And here maybe we could do a simple exercise. So I will create a new model. I will also open default layout. So I clicked on File. At first I clicked on New File, and then I choose from File, Open Default Layout. Maybe you will see this one, and you need to switch to Network Editor, but my default network shows always the Network Editor because I saved this setting, like you can see right now, as my default network with save as default network. And after that, always when I open default layout, I saved it as I saved the layout as default in the past with this setting, with this composition, and now always when I open this default layout, I get that setting and composition I saved before. Okay, we talked about headway based on leading vehicle class. So let's do a simple exercise with one link. Could have 300 or 400 meters. And on this link, we will put some conventional vehicles and some automated vehicles. So at first, we'll create our own vehicle type, AV for AVs, and vehicle class for AVs. For that, I go to base data, vehicle types. I select here car, and I duplicate it. I will rename it to core AV. So I went to base data, vehicle types. It opens the list for vehicle types. I selected core here. I choose from the context menu, accessible through right click, duplicate, and then I renamed core to core AV. And similarly, I go back to base data and vehicle classes. And I duplicate my class core. And I will rename to core AV. And one more thing here is important. To a vehicle class, you can assign vehicle types. So to my new class, I will deselect here number 100 core, and I will choose 630 here, in my case, core AV. So for the vehicle class core, I have only vehicle types 100 in, and for my vehicle class core AV, I have only vehicle type AV in it. Okay, I will put a vehicle input on the link with some high volume. And you can see there is a default, there is a vehicle composition default. These settings you can change under traffic and vehicle compositions. So at first I put the vehicle input on the link and put some high volume there. And a second I will go to traffic and vehicle compositions. And here, let's say I want to have a 50% conventional cars and 50% my AVs there. So instead of AGVs, I will choose here car AV. And here relative flow I will set to 1 for both of them, so I will have 50% cars and 50% AVs. So when I try to run the simulation, at first I need to save the network, and then with the plus or minus button you can speed up or slow down your simulation. So when I pause the simulation and I select one vehicle here, I can check the vehicle type in the quick view window. And this is core AV. This is core AV. This is core. And maybe I could use a color scheme just to distinguish between the vehicles easily by color. So I can do that in edit graphic parameters for vehicles in network. And it's the drawing. I change the drawing mode from color by distribution to color by scheme. And color scheme configuration, the next line here, you can choose here an attribute which will be used for the color scheme. And we could use the vehicle class number or the vehicle type number, because we have one-to-one settings for vehicle types and classes. So I will scroll to vehicle type here. And then I should find here number, vehicle type number. And then here I will, from the context menu, I will add one more line. And if I remember correctly, then yeah, I can see it here. My vehicle type core has number 100. And I keep the white color here. And for vehicles with vehicle type number more than 100, I will choose red color. So this is a core. And this is an AV. So now you can see I will switch on also the legend here, legend on off here on the button. And I need to add that the vehicle color into legend here, into graphic settings. So I have a core and AV. Like this. So a quick recap. I created a new vehicle type by duplicating the existing one, and I rename it. Then I created a new vehicle class by duplicating existing one and renaming it. And I change the settings, which classes belong to this, which types belong to this vehicle class. And then I set the colors for vehicles by editing graphic parameters for vehicles in the network. For driving mode, I choose use color scheme. And on the next line, there is a color scheme configuration. Here I choose an attribute, which is a vehicle type number. You can find the vehicle type also here directly, but this will be in a different form. This is not just number, but this is 100, for example, 100 and the name of the vehicle type. And for the classification for the color scheme, you need some values only. So I scrolled down to vehicle type, to relation to vehicle type, and under vehicle type you can find number, and this gives you, or this is only the vehicle type number, so not the string with the value and the name, but only the number. And then from the context menu, I added one more line here, and I set the upper bound to 100 because I know that my vehicle type number for cars is 100. and for AVs I have a higher number. So with these settings you can distinguish between cores, you can see here, and a quick window, and the red ones are AVs. Okay, and now let's say that this link uses driving link behavior type number 3, which is a freeway, and I open from base data and driving behaviors the list of driving behaviors. And I open number 3, freeway. And on the tab car following model, I want to change some parameters based on the leading vehicle class. But I forgot one more thing. I need my conventional vehicles will use different driving behavior than my AVs. So if my conventional vehicles should use this number 3, then let's say I will duplicate this, that my AVs should use this I created, number 104. And I need to go to base data and link behavior types, because here I can say what happens on a link which is using the link behavior type number 3. And by default, vehicles are using driving behavior number 3, but I can define an exception here, or a specific driving behavior for a specific vehicle class in the coupled list for driving behaviors. From the context menu, I choose add, and for my class core AV, I say this should use my AV behavior. So all other vehicles will use number 3, freeway, but this specific class will use driving behavior number 104. So this is the setting for link behavior types. And I go back to driving behaviors, and I open the new driving behavior I want to use. They should be used by my AVs. And here I can add a line, and I say that if this vehicle, this driving behavior will be used by my AVs, and if this AV is following another AV, in that case, I want to reduce the CC1 distribution and also CC0. So I will set CC0 to 1, and let's say I want to have CC1 0.3. It's not here, that option, so I need to create that under base data, distributions, and time. I can take the first one and duplicate it, and I will change the name, and I will change the mean value to 0.3. When I have this, I can go back to driving behaviors, and I will choose that time distribution here. And let's see how it looks like in a simulation. And you can see here that if AV is following another AV, the distance is much smaller. It's just based on 0.3 seconds time gap, but the distance of AV to conventional vehicle is higher. It's the default setting. and the distances between conventional vehicles are by default, and also from conventional to AV is by default. So if there are AVs, if there is AV following another AV, then the gap can be such small. Of course, it's based on the speed, because we define the time gap. So quick recapitulation of my last steps I did. At first, I changed the link behavior type for the link to number 3 freeway. Then I opened the list for link behavior types, and I add in the capitalist driving behaviors for my AV vehicle class, I assign driving behavior number 104 in my case, which should be used exclusively by this vehicle class on each link which is using the link behavior type number 3. And then in driving behavior list, I set for the driving behavior used by my AV different CC 0 and different CC 1 when such vehicle class is followed. So this is the way you can do it. I see questions in a chat window. Can the driving logic of CoEXist applicable for simulation on motorways? Yes, of course. You can use Wiedemann 74 and Wiedemann 99, and actually these 3 driving behaviors. Oops. Let me correct this. This new 3 driving behaviors, which are available in Vissim 2020, always when you create a new model, these are based on Wiedemann 99, which are suitable for motorways, and you have here much more parameters to set. You have much more control of the behavior than with Wiedemann 74, which is usually used for urban environment, but it's not a must. But it's also used for viewing areas, for example, or merging areas. So you can use both of them, and it's applicable for motorways and also for urban environment. Okay. Let me check the time. Okay, I will go to the next one, and that's platooning. This is the newest one we implemented into Vissim, and there is a built-in feature in Vissim you can use to simulate platoons. So you don't need to use scripts for that. And the use case here is to simulate effects on general traffic, and there is no simulation of platoon internals, so there is always stable driving. And there are new driving behavior attributes for platooning. A few more details. It's a vehicle class specific, which means that you can have platoons built from cars and platoons built from AGVs separately, or you can have mixed platoons. It's up to you. And it's also lane specific, which means you can activate platooning only for one lane or for selected lanes. Some details. For joining, if a vehicle can join a platoon if the vehicle is driving in the same lane, and if the speed of this vehicle is higher than the speed of the platoon, because only in that case the vehicle can approach the platoon. A vehicle will not accelerate over its desired speed only because of catching platoon. And it doesn't work for, or it's not designed for public transport routes or parking routes, but only for static routes. The platooning parameters we implemented, you can set the number of vehicles, the maximum number of vehicles in a platoon. You can set the maximum desired speed for the platoon. The platoon drives always with the speed of maximum desired speed of the platoon or of the desired speed of the platoon leader. If the desired speed of the platoon leader is smaller than the maximum desired speed for platoon, then the platoon drives with that smaller value. Other way around, if the maximum desired speed for the platoon is lower than the desired speed of the platoon leader, in that case, the platoon will drive with the maximum desired speed of the platoon. Always the lower value from these two values is used. So maximum desired speed for platoon or the desired speed of the platoon leader. Then there is a maximum distance for catching up to a platoon. There is a gap time you can set for vehicles within the platoon, and the minimum clearance you can set here. For driving, the platoons do not do any lane changes. And the vehicles keep same distance, which is speed dependent, and there is a limited acceleration change. And the parameter of a platoon, they can change if a platoon drives from one link to another link, because driving parameter is a setting of a link, or for a link you can set the link behavior type, and for a link behavior type you can set the driving behavior. So if a platoon go from one link to another link, the parameters can change. For example, if you can imagine a situation that your platoon is driving from an urban environment onto the motorway, and you want to have different parameters on the motorway than you had out of the motorway. And platoon will split automatically if needed because of red signal. So if not all vehicles from the platoon can make it through the green signal, then the platoon will split. When a vehicle needs to leave the platoon, then the distance to the vehicle in front and behind will increase continuously, and the platoon will split. After that, the vehicle can make the lane change. How we deal with platoon stability? Each platoon has a platoon leader, and there is always a last vehicle in a platoon. And this last vehicle in a platoon proceeds to keep defined gap time and clearance to preceding vehicle, and its acceleration is limited to acceleration of the leader plus minus 2 meters per square second. And the platoon members, the vehicles in between, they are distributed equally. So that's the way how we deal with platoon stability. It's a simplified model, and which means that there is no real communication or simulation or communication process itself. So the vehicles are not sending any packages, and there is no dealing with latency. So there is an assumption that the platoon is stable, that the vehicles have equipment which allows that. Platoons can form, for example, in front of a signal. Then if a vehicle needs to leave the platoon, so the distance increases, the platoon will split, then the vehicle leaves the platoon. And now we have two platoons in the network, and the second platoon can catch up with the first platoon and can rejoin. So not only vehicle can join a platoon, but also platoon can join another platoon. And then if there is a signal and not all vehicles can make it, then platoon splits. And the same if there is unsignalized intersection. But this time for platooning, you should use priority rules, not conflict areas. Let's have a look on Vissim, and let's open another example from platooning. I see the question here, how is the leader of the platoon decided? Platooning can be allowed for a specific driving behavior. So I opened the dialog for AV regressive, and here on the type autonomous driving, you have platooning possible option. And if this is activated, it means that vehicle which uses this driving behavior can form a platoon. And if there is another vehicle approaching this vehicle with the same driving behavior, then they can form a platoon, and the first vehicle in this form will become a leader in a platoon. So a leader of the platoon can be any vehicle which is using driving behavior where platooning is possible. And if it happens that another vehicle joins this vehicle into a platoon. So you can run the simulation here. It's the same I showed you in the video. Use plus or minus buttons to speed up or slow down, or use F6 on your keyboard to pause the simulation, and you can press F6 to have step-by-step simulation. And here you can see that the platoon splits into two platoons because this vehicle has different route. All other vehicles have the same route, so they could stay in the platoon, but not this one. And then the second platoon can join the first one later, as I showed. You can try to do some change. For example, you can limit the number of vehicles to 3 to see the difference. You can see now we have 2 platoons instead of 1. And when you select a vehicle in a platoon, then you can see that this vehicle has an attribute index in platoon. And if the index is 1, then it's the leader. And if index is higher than 1, then it's a platoon member. And you can see that the color scheme is used here to distinguish between the leader and the member. So the same principle is used as I showed before. So the drawing mode is use color scheme, and the color scheme configuration uses the attribute index in platoon. And if it's 1, it's dark blue. If it's more than 1, it's light blue. So there is another question in the chat, how a conventional car can pierce to a platoon of several AGVs or even passenger cars, how it can communicate with them or send a signal. What is the maximum length of a platooning in this case? So the maximum length of a platoon you can set by number of vehicles here. And then the maximum you can enter here, I think it's 99,999. So you can control the length of a platoon by the number of vehicles in the platoon. And it works. It works this way. I start again the simulation. This is the first vehicle driving in the network, and it's not in a platoon. And there's another vehicle which is approaching this one. And after this vehicle reaches the distance or the gap which is defined for the platooning, then it becomes a platoon member. It creates a platoon with the first one now at this moment, because the gap and the clearance is as defined for platooning. Here is a gap time and minimum clearance. And both of these vehicles are are driving by the same driving behavior, so they can form a platoon. And there is a next vehicle approaching this one, and it's also capable of platooning. So when it reaches, when it fulfills the conditions, it becomes a platoon member. And again here, this vehicle approaches this one and becomes they create a platoon. This can happen not only when the leader is standing. This can happen also while driving, but for that case, always the second vehicle, which is approaching the first one, must drive a little bit faster than the vehicle in front. It is not sending any message. It just can recognize that there is a vehicle within a range in front which is capable to form a platoon. And when it recognizes that there is such vehicle, it will approach this vehicle in order to achieve the time gap and the clearance which is defined for platooning. And when that happens, then they form platoon. Okay, this is the simple example. There is also one more example for platooning. When you open a file and when you go to the directory with examples training, it's this directory, or more easily. When you go to help and examples, then you can choose open training directory. And here under autonomous vehicles, there is platooning built in, and open this one. I just start a simulation so you can see what happens here in this example. This is the Helmond network with some fixed signal controllers, and the platooning is activated for a portion of vehicles in the network. So not all vehicles are platooning capable, but a certain percentage of them. And what you can see here in this example, there is a chart which shows you the number of vehicles in a platoon in total in the whole network. You can see the number of platoons in the network and number of platoons with 2 vehicles, with 3 vehicles, with 4 vehicles, so number of platoons of different size. And this evaluation is done by a script. So in the list of scripts, you can find one. So when you double click, it should open in your text editor if you define a text editor for in Windows. And you can see that this script is very simple. So just let me explain how it works. This will give you a group of vehicles which are in a platoon, because it filters all vehicles with attribute index in platoon if this value of this attribute is more than 0. And then this will count how many such vehicles are there. This will count vehicles with index in platoon equals 1. So how many leaders are there, which means how many platoons are there in the network. And then you can check how many platoons are there in the network with index by counting vehicles with index in platoon 8. And then if you want to calculate how many platoons of size 7 are there, then you need to count the vehicles with index of platoon 7 and this minus number of platoons size 8, and so on. And then you can show these in Vissim, and you can see how the values are changing there. So I switch back to my presentation. I already mentioned the attribute index and platoon. There will be also 2 more attributes with the service spec 7. There will be also attribute platoon leader number and platoon size. So these informations will be available for each vehicle. One more feature we implemented, which is not necessarily only AV feature, but it allows to model shared space like areas where the vehicles in the dynamic potential can be recognized now, and the pedestrians can actively look for gaps between vehicles and can use them. So they are not just standing like here on the left side. If there is a vehicle in front, they don't look actively for some gap. They just stay there and wait on the left side until there is a gap in front of them. But here on the right side, then you can see that each pedestrian goes to the nearest gap available and then cross the street. So they are actively looking for gaps on the right side and are crossing the street. For this, there is also example. You can have a look on it. I will go back to my examples. Is this one consider vehicles in dynamic potential? So when you open this example in Vissim, then you will see the same scene, and you can have a look on the modeling technique. But I will not do that at this moment. I would continue. I have just a few slides, so I will be finished with the presentation in a few minutes, and then we can go through your questions. So there's also possible to define 0 passengers for AVs which are driving without driver and without any passengers in the network. It was not possible in the past, but now it is. There is also OpenDrive import. OpenDrive import is open file format for logical description of road networks used often also by car manufacturers or startups and so on. So some companies can do some scan of a real road and provide a file which you can import in Vissim, but the import is restricted to links and connectors. And if you would like to try it, then look for OpenDrive, and then you can land on OpenDrive Home, and there are some downloads. And there are examples. There are some example networks, and you can just download it into your Vissim. And in Vissim, you can choose File, Import, OpenDrive, and it creates the network in Vissim. Okay. Driving behavior parameters. In Vissim, when you create a new file, and when you open the list of driving behaviors, then you can find here always these 3 new driving behaviors we defined within the CoEXist project for 3 different driving logics: cautious, normal, and aggressive. And for each of these, we changed the values of the driving behavior parameters for car following, for lane change, for lateral signal control. And you can use this as a starting solution if it fits your assumptions about automated vehicles, or you can change the parameters. So in our CoEXist deliverables, we defined what we expect, which way the parameter should be changed for each driving logic. If the value should be the same or smaller or higher than the default value, which is used for conventional vehicles in Vissim. And we did it also for lane change attributes and signal control. Very few words for cooperation and communication. The first question you should answer as a modeler: what is the impact of communication and cooperation for the vehicles you want to have in your model? So if the impact of communication and cooperation is that the vehicles can keep much smaller gaps to other vehicles or can accept smaller gaps at intersections and so on, in that case, you can do the changes. You can change the driving behavior parameters for your vehicle class. If that should be something much more complex, like a cooperative behavior, in that case, you need to reach or you need to use an interface. So that's the second question would be, can I replicate the expected behavior with standard PTV Vissim, or do I need an interface? So if you get the expected result by changing parameters in Vissim, then fine. If not, then you have the possibility to use interface. It could be COM. You can use to read or set attributes or create objects, manipulate them. This could be used for vehicle-to-vehicle communication or vehicle-to-infrastructure communication. There are already examples under examples training and autonomous vehicles. There is another interface called driver model DLL, which can replace the internal following behavior model of Vissim by own algorithm, and optionally you can have also own algorithm for lane changing and or algorithm for reaction on signals. And the third one is driving simulator, where you can couple own control algorithm, so you can have a full behavior, full control of the behavior, and you can couple it with Vissim, and you can have optional integration of vehicle dynamics there and sensors if you use some third-party software which can do this, like a pre-scan or a car maker. In such case, it's so-called nano simulation. Materials you can find in the directory where your Vissim is installed. Then under API, you can find driver model DLL and driver simulator DLL with some examples. There is also COM help and examples and some recommended examples there. Okay, your questions on modeling problems. So let me have a look. Let me have a look on the questions here. Regarding interaction phase, what do you mean see or interact? What information is sent or received? Can we use this feature for vehicle-to-vehicle or vehicle-to-infrastructure or not? So when I said that the vehicle can see or interact, each vehicle, when it drives through the network, can react on objects and vehicles. And which objects and vehicles are visible for this vehicle, this is controlled by parameters in the driving behavior. So, and if this can be used for communication, so some kind of communication, yeah, for each vehicle in Vissim, let me see you that. Let me show you that very quickly. So when you select a vehicle in the simulation, then in the quick view window, you can go to attribute selection, and in this you can look for interact and add these attributes here, and you can see the interaction state of the vehicle and the interaction target number and the interaction target type. So at the moment, this vehicle is interacting with a vehicle number 3, which is this one here, and it's in a following state. And if you would like to use this information somehow for communication or for some actions, then it is possible through COM, because you can read the values of the attributes or of every vehicles. So if you would like to do some scripts which would do some actions, then you can access these values. So let me have a look on another question.
Hi, Peter.
Yeah.
Yeah, thank you. Thank you for the great demonstration. Would it work if I read some of the questions to you, and then you don't have to go back and forth?
Okay, perfect.
Yes, so we have one on can the interaction vehicle configuration also be applicable for lane change? That is, can the vehicle interact with vehicles while making lane change and react accordingly?
Yeah, okay. Yeah, for lane change, there are different attributes which can be set and change. So if you want to control or to change the lane change behavior, then this is the place where to do that.
Okay, but then it's possible then while doing lane change, they can react still to the vehicles being seen ahead, of course.
Yeah.
Okay. Another question was, what happens if the minimum look ahead distance is set to 0? Would no leading object then be observed?
If you set the minimum look distance to 0, that's the default settings. In that case, these two numbers are important. The settings here says that the vehicle can see 2 objects, and the number of interaction vehicle is higher. So if it has 2 vehicles in front, 2 vehicles can be seen. If there is 1 vehicle and 1 signal head, then this 1 vehicle and signal head are visible. So you can here set and change, in this case, up to 10 interaction objects are visible. When you limit this, when you say only 5 vehicles, this means only 5 vehicles, but up to 10 interaction objects. So this can be 0 for a lane-based behavior. It's the default setting. But if you have a non-lane based traffic, or if you have many objects, for example, if you have a mixed flow, so there are lanes for vehicles, but there are also cyclists, and you can have 5 cyclists in front of you, at the same link positions, because they use the whole width, for example, at the intersection. So they are not following each order like the cores, but using the whole width. And in that case, you might need to increase the look ahead distance to be able to see all objects within this distance.
Okay, perfect, thank you. Another one with regards to implicit stochastics, when it's not checked, where can the modified deterministic variables then be altered? And in your example, what assumptions did you base your deterministic distributions on?
In my example, so let's have a look. That was about implicit stochastic.
Yep.
So in this example, when you have a look on vehicle composition that I'm using here, vehicle type 100 energy arc, I'm not using inputs here because I'm inserting the vehicles here by script, and there's a type 100 here, and there's 1, 2, 3, 4 there. Okay, let me check what vehicle type is this. Okay, it's 100 core, and when I have a look on vehicle types, 100 is using number 1 of acceleration and decelerations. And these are reduced to the median. So in all of these, in this example, I reduced to the median to not have the spread of values, because the minimum, the line which represents the minimum and the maximum here means then each vehicle will get a value within this range. So I reduced the range so each vehicle can get the median value. And additionally, the implicit stochastic is switched off. I don't know if that answers the question, but if you would like to know more about this, or if you wanted to ask something else, then please send me that question with more detail. What you meant with that to my email, and I can answer that afterwards.
Perfect. Yeah, thank you. Let's see. Let's read another one. With regard to platoons, one of our participants is asking whether a conventional car peers into a platoon of several heavy goods vehicles or even passenger cars, whether there can be a communication with them or send them a signal to peers within them.
So if the question is if another vehicle can join a platoon from a side, that is not possible. a vehicle can join a platoon only from if it's in the front of a platoon or behind a platoon, but in the same lane. In that case, when it is able to approach the platoon, so if its speed is higher than the speed of platoon, so when it can catch up the platoon, in that case, it can join the platoon. But if the vehicle is in a neighbor lane, it cannot join the platoon. The vehicles in the platoon will not make space for such joining vehicle. They will not make space in the middle to allow joining for third vehicle. And
also,
no vehicle can go can change the lane into a platoon. That's not possible. That's blocked.
Okay. So in that sense, also no conventional vehicle can go through the platoon and sort of like if they wanted to change lanes, right?
A conventional vehicle which is not capable to form platoon can just follow the platoon or can overtake the platoon on the neighbor lane.
Yeah. And what is the maximum length of the platoons in this case?
The platoon length is set by the maximum number of vehicles in a platoon for this driving behavior.
Perfect, thank you. I think, looking at the time, we still have some questions, but we will address them with our follow-up email, which we will also send together with the slides and recording of today's training. Some final words from your side, Peter?
If you keep this call session open, I am willing to stay here. If someone would like to discuss something with me, then I'm happy to do that.
Okay, so do we have any comments? The audience, feel free to unmute yourselves and pose some questions for Peter. We also have the chance, if you would have any troubles with the exercises and you would like to share your screen and go through them shortly with Peter, also please let us know. I can assign the screen sharing capacities to you. Yes, shoot up. I see that you have unmuted yourself.
Yeah, can I ask you a question? Peter,
yeah, sure.
Question? Yeah, thanks for your wonderful presentation. It was really great. My question is regarding the CoEXist driving behaviors or driving logics in PTV Vissim.
Yeah.
I think as I read the CoEXist document, the data was collected with regards to car following and not major lane change was carried out. So on what assumptions did the PTV recommend the values for lane change or lateral control?
I understand. It's true that we collected a lot of data on the test track in Helmond, but all the vehicles just followed each other, and we didn't have data about lane changing. But we did some recommendation for lane change parameters here. But all our recommendations are based on assumptions, and we tried to assume how a vehicle using this type of driving logic should or would behave. I mean conceptually. That means if we have a normal driving behavior here, and we said, okay, this one will have similar values to the human driver. So we kept the values as they are for human drivers, and we assume that the cautious vehicles needs much higher gap time or much higher distance, and because it's much more cautious, and this reflects also the values for lane change. So they are more cautious, less aggressive. And the opposite is for aggressive. For them, they expect we expect a little bit more aggression in lane changing behavior. So we proposed different values. For example, the safety distance reduction factor. So the more advanced AVs can use smaller safety distances for merging, for example, into a lane. So that was the basic assumption, that the aggressivity we expect, which we can define in form of safety distance or following gap or clearance and or acceleration values and deceleration values. So that was the idea we followed. We would be happy if we would have some empirical data about lane change from automated vehicles, but these are simply not available. And we also didn't have algorithms from OEMs, from the car manufacturers, if they would be willing to share their algorithms for lane change, if they have them, because that's also a question. Then we could incorporate them into our model, of course.
Okay, great.
Can I just add one thing there? So
Sure.
I think it's important to also mention that, of course, you could do as Peter said about making experiments on test track today, but on the future automated vehicles, not even the car manufacturers know how they will behave when we reach actual level 4 capabilities. So the conceptual driving logic is the cautious, normal, all-knowing, and trying to capture potential different driving behavior in the future. So in that sense, you have to rely on assumptions, as Peter said.
Yeah, I agree with that. Yeah. Yeah. I have one last question.
Yeah.
Is it possible? Yeah. Okay. During the test trials, like I'm just making a connection between SAE and driving logics. And during test trials, I think like level 2 automation was used. And with regards to the driving logics in the PTV Vissim, the lane change as well as the lane following is used, like the automated driving system is used. So does it mean that these driving logics kind of relate to level 3 or level 4?
No, I wouldn't say. We didn't work with automation levels in CoEXist, because if you say it's level 4 or level 5, it doesn't say you how the vehicle really behaves, how big the distances to other vehicles are, how aggressive the vehicle is. It just says you if the driver, if the human is in control or not, and what can the vehicle do in means, if it can do lane change or not in automated mode. But that's not enough for our simulation. So I wouldn't say that the representation that the driving behavior implemented or added into Vissim is level 2, because you can have any level, I would say, regarding the following behavior. Because if level 4 or 5 means that they can drive fast and they can drive at small distances to other vehicles, then you can have such behavior in Vissim. So it's not limited. So that's why we have the concept of 4 driving logics we called restive, cautious, normal, and aggressive, because the description of this behavior tells you more about what you can expect in the behavior, not about who will be in control, a human driver or the computer, but what you can expect when you have a look on the street and you have a look on the position on the vehicle and on the action of the vehicle.
Yeah, makes sense. Thanks. Thank you very much.
You're welcome.
Yeah, that's it from my side.
Okay, anyone else wants to share a question? Okay, otherwise, I wanted to remind you that we're gonna. Yeah.
Sorry, Daniel.
Go ahead.
I would like to use the opportunity, if some people are still here connected, I would like to ask how do you perceive such training session or such workshop? How useful is this for you, or what do you think about the timing? We spent more than 2 hours together. Is it okay to have such meeting for 2 hours, or would it be better to have more shorter sessions? What is your opinion on that?
So if you have any feedback on the workshop, please let us know in the chat box or unmute yourselves, as Peter was saying, on the length and the level of detail, or any comments you would like to share with us. That we'll be very grateful for it. So we have one comment. I think it works, but maybe a brief break halfway through would be nice. That's true. We could also have taken. Yeah.
So next time, you, Daniel, you need to stop me for a break.
Yeah, yeah, will do. All right. But I think it was a really great workshop. Thank you, Peter, so much. Very detailed and understandable, and I hope people were able to follow you through the execution of the exercises. We also had some interesting comments in the question box. Comments are coming in. Some say that it has worked well, that maybe 2 hours it's a bit long, that maybe shorter sessions would be more manageable to concentrate. But okay. It was really good. I think the workshop was similar to a previous one in YouTube, with some additions compared to the previous one. One more comment, shorter sessions might be better. Each session focusing on one topic, okay. But on all, I think, yeah, it was a great training, Peter. Thank you very much. And thank you for everyone who joined, also for your patience and participation. Do you want to say something more, Peter?
Yep, thank you for your attention, and I hope it was useful for you, and have a fun using Vissim. And stay healthy.
Exactly. I hope you stay healthy. You can join us also today in our afternoon session with part 2 of the CoEXist final conference. So again, thank you everyone, And please contact us if you have any further comments on our session today. You will receive recording and slides in our follow-up email. Okay, thank you so much. Bye bye, everyone. Thank you, Peter. We'll close it now then.